So today's the first class for calculus 3, and I'm going to give a quick review on vectors and their related topics. Okay, so for vectors, okay, how do we describe vectors in the space? Well, you can describe vectors in two different ways. First, it's just an object in three-dimensional space or two-dimensional space. It has a starting point and ending point. That's called a vector. It's in three-dimensional space. It's an object. Okay. Now, in mathematics, we have to use the numbers to describe something, like a coordinates to describe a vector. So this is a vector in three-dimensional space. Okay. So what I'm going to do is all the vectors can be in different locations. Some vectors are parallel, some vectors are not. Like these two vectors in the space, okay, they are identical, but just the different location, the same direction, the length is the same, right? There's no big difference. So in order to describe vectors, we put the coordinate system here. Okay, we put the coordinate system. Okay, this is axis, y-axis, z-axis. Then you give me any vector in the space, I can move it to the origin. The starting point will be at the origin. Okay. Then this vector, I can use three numbers to describe it. So the point, this tip of the vector has coordinates, right? Called A and B and C. Okay, those are the coordinates of the point at that particular point. The point is different from vectors. Okay, so this is a point. Here's, yeah. And vector, usually, there are many ways to describe vector. So if this is a point is O, origin, and this point is P, and this vector is denoted, this particular vector is denoted by OA, okay? And if, okay, the coordinates of the point P, that's a point P, are A and B and C, then it is usually denoted by the following notation. Okay, always a slight difference here. Okay, so when I use three numbers to describe a vector, then that vector, this is a notation, okay? Parenthesis, curved parenthesis, that's for the coordinates of the point. Right? So then, okay, we can, yeah, in two-dimensional plane, you only have two components. That's a typical example in three-dimensional space. Okay. 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 So this vector, after we moved it to the origin, we have the name for that called equivalent representation of that vector in the space. Okay, so OA, okay, yeah, we have a point. Okay, so this is if this vector coming from that vector from A and B, so that vector is denoted by A and B. Okay, from A to B. Okay, so if I move, if OP is obtained from AB and moving it parallelly, okay, to the origin, then yeah, if, okay, OP is obtained from moving OAB parallelly to the origin, then OP is called, the name is called, yeah, it's called equivalent representation of that. Representation of AB. Sometimes you say start at its origin. Okay. So the equivalent representation at its origin, that vector is unique. Okay, right? So because that's only one there, you know, the direction is fixed, the length is fixed. Okay, so those are the notation. And then let's take a look at example. Okay, we are given A 0, 3, 1, B 2, 3, -1, right? Okay. We want to find out AB and the equivalent representation of the vector at its origin. All right. So first of all, right, you find those 2 points, X, Y, and Z. Okay. Well, 0, 3, 1. Where's the point? X is 0, Y is 1, 2, 3, Z is 1. Okay, so that's the point A. Right? And the 2, 3, 1. 1, 2, 3. 1, 2, 3. And the -1. So that is a B. So this is a vector. Okay. If you want to make it looks like, okay, so actually how can I get it? So this is a, right? So you can visualize it's below the XY plane. It's below the XY plane. Okay. So this is a vector in the space. So that's a vector. It's AB vector from A to B. Okay. Now I want to parallel translate to the origin. Okay. And then that's point O here, right? So this vector is parallel to AB and yeah, starting from its origin. Okay. Now the formula is very simple. The vector equivalent to the vector from A to B is all you have to do is just take the difference of the 2 components. Okay, so that's just 2 minus 0, 3 minus 0, -1 minus -1, which is going to be 2, 3, -2. Okay. 2, 3, it's a 3, yeah. So it's 2, 2, 0, -2. Okay. So the relationship between OP and AB is the components. Yeah, if this is going to be, I'm going to say A1, A2, A3, that's a B1, B2, B3. Then the components here is going to be B1 minus A1, B2 minus A2, B3 minus A3, okay? I just take the difference. Okay, that's how do we solve the problem. All right, so now for vectors starting at its origin, you can do the addition and subtraction. Okay. So here yeah, addition and subtraction, that's how do we do it? Okay, here's a picture. So if we have a vector, okay, if we have a vector, I'm going to use a notation U, another vector using V. Okay, so U is going to be U1, U2, U3. V is going to be V1, V2, V3. Okay. Okay. Then formally we can define the sum of those two vectors. Okay. So those two vectors, first of all, you view them as like objects in the space, but starting from the origin. Now you can do addition. You can add them together. Okay. You add them together, all you have to do is just adding the corresponding coordinates. Okay. And if you want to do the subtraction, you can just, yeah. Minus V3, okay? You can also do the scale product. Lambda is a number, okay? And this is going to be lambda U1, lambda U2, lambda U3. Now, so you get a new vector. The new vector, you get a new vector. How the new vector is related to the original two vectors, okay? So here's the idea, okay? So this is a picture I'm going to show you. So you draw a parallelogram in the space, okay? So this vector is going to be the vector U plus V, okay? So U plus V is there, okay? But you can use a geometry picture to define the addition. Okay, so there's two definitions here. One is the geometric definition, the match, okay? One is the algebraic definition. Add the two vectors together. Okay, so you can do the addition, multiplication. Okay, so how about U minus V can be viewed as U plus negative V, right? So where's the negative V? Negative V is somewhere here, negative V. So when you add it together, so this will be the vector U minus V, right? Again, you can use the parallelogram to define U plus negative V. But that way, from the geometry, you can see that this is actually is a vector from yeah. So actually, this is a vector, this is a diagonal, okay? So U minus V, that vector, is a equivalent representation of the vector from this tip to that tip, the diagonal, okay? Now, lambda times U depends on lambda is positive or negative. If it's lambda is 2, then 2U means you double the length of U, the vector U. Okay, so here if this is a U, and that would be 2U. Okay, just double it. So you understand the multiplication. So those are the vectors. Now we're going to also introduce special vectors. Special vectors I is going to be 1, 0, 0. Okay, J is going to be 0, 1, 0. And K 0, 0, 1. Those are determined by the coordinates. Okay, those are determined by the coordinate line. Okay. Okay. If you want to look at where it is, this is a picture. So this axis, this y-axis, this axis. So this vector is I, that vector is J, and that vector is K. Okay. I, J, K. Those are special three vectors. Now, since we already defined the addition, multiplication, scalar multiplication, so we can express every vector as a linear combination with the three. Okay. So if we have a vector, if we vector U, right, U1, U2, U3 has three components, I can first of all, I can separate them. Then each vector, U is U1 times 1. So I can take U1 out. Okay. Great. Yeah. So this vector U1 can denote by I, U2 can denote by J. I'm sorry. Right. So in other words, in a vector, like 2, 3, -1 can be simply written as 2I plus 3J minus K. Okay. And if the those are the vectors in two-dimensional space, it's a similar. You just have two components. You don't need to measure the third component. Okay, because third component is always 0. Okay. Now we can talk about the length of the vector. Okay. The length of the vector okay, if it's U, U1, U2, U3, and the length of vector is denoted by this. And this is actually the square root of this square. The sum of the squares. Okay. It's always a non-negative number. Actually, this is actually, if you look at the picture, okay, if this is a vector, here's O, here's a P, and this is this U vector is denoted by O from O to P, right? So this is actually the distance between O and P, okay, geometric. All right. So now, all right, so take a look at examples. Okay, we have the vector U, 1, 2, 3. We have another vector. Okay, we have another vector 3. Yeah, 4. Okay, 5 and 3. Okay. So we want to find out 2UI plus V, 3V, okay? And We also want to find the length of the difference of these two vectors. All right, great. So the first, just straightforward, right? So it's 2 times 1, 2, 3, and 3 times 4, 5, 3. Okay. Now, here's only algebra, just multiplication, subtractions. I tried to teach a fourth grade student about this, and they can understand easily this part. Of course, not derivatives, because that's a good practice for them to do the addition multiplication. Okay, just put a bunch of the numbers together instead of like 2 times 3 and 2 times 3 numbers. They can do that. Okay, it's not just be careful. You see, you cannot just forget. Don't forget the second one. 2 times 1 is 2. 2 times 2 is 4. 2 times 3, 6, right? And plus 3 times 4, 12. 3 times 5, 15. 3 times 3, 9. Then you have to add the corresponding number together. Okay, 2 times plus 12, 14. 4 plus 15, 19. 6 plus 9, 15. Okay. All right, so in order to find the value of the second one, is first you have to find the difference of those two vectors. The difference of those two vectors, okay, it's 1, 2, 3, right? Minus 4, 5, 3. So first 1 minus 4 is -3. 2 minus 5, also -3. 3 minus 3 is 0. Okay. Then the length of this new vector is going to be -3 squared plus -3 squared plus 0 squared. Then answer is going to be 3 square root 2. Right? So it's when you do the homework, it's important to show all the steps clearly, step by step. Don't just focus on the answer. We want to see the solution, not the answer. Okay, answer, most of the problem have the answer key in the back side of the book. You should learn how to express all the steps clearly. So when on the test, the quiz, if you show some key steps, then even the answer is wrong, you get most of the partial credits. Okay. Now, what is the geometric meaning of this, the norm of the difference of two vectors? The geometric meaning of these two vectors, the norm of those two vectors is, suppose this is a U, okay? And suppose this is I just sketched it, not exactly. So the U minus V is actually this vector, okay? So it's parallel translate. So actually is a distance between those two, between these two tips of the vectors, okay? So that is a distance 3 square root 2, okay? Yeah, because this is a vector here. And that vector is equivalent representation of the vector from the end of the V to the end of U. Okay, And so that is the picture. All right. Now for the vectors, we also have another important notion called a dot product. Okay. You have two vectors. Okay. The two vectors, let's denote. Okay, so the dot product is going to be the sum of the products of the corresponding terms. So U1 times V1 plus U2 times V2 plus U3 times V3. Okay, so that is dot product. Okay. In mathematics, we have very important inequalities. It says that we call the Schwarz inequalities. U1 V1, U2 V2, U3 V3 square is less than equal to U1 square, okay, plus U2 square plus U3 square, and V1 square plus V2 square plus V3 square. Okay, and the equality holds. Equality holds if and only if one vector is multiple of another vector. Okay. Okay. Equality holds if and only if U is parallel to V. Depends on which one is not. If one of is not zero, then U is going to be a multiple of V. Okay. So if V is not zero, okay. Okay. So that is but if I translate that inequality to an equality for vectors, okay, then you have this. Okay. If you remove the square, so you get this. Okay. Okay. So that is the inequality. If I divide both sides by I have this. So I get a number which is smaller than what? Smaller than or equal to 1. In other words, if I remove the one on the top is actually the absolute value. It's not the length of the vector. It's not the vector. The dot product is already. So this gives you this inequality, right? Without the absolute value. All right. So there is a unique angle. Okay. There is a unique angle theta between 0 and pi such that, okay, this, okay. If you give a number, the number could be, it's between negative and the positive one. Then that number, yes. Okay, no problem. Yeah. All right, so in fact, this is the angle between those two vectors. All right, yeah. You can show that this must be the angle between those two vectors. Yeah, I'm not going to show this here, but let's use that to find the angle between two vectors. Okay, so let's see. So we are given two vectors. The vector u, here's -1, 3, 4. Another vector, 5, 2, 1. All right. Find the angle between u and v. Okay. This is a 5. Okay, 5, 2, 1. All right. So you think about what you should do. Next step. Okay, you are given the formula. Right. So to solve this problem, in order to get as much partial credit as possible in case you make mistakes, step 1, write down the formula. Okay, because this is the formula you're using. Don't hide it. So this is the formula. Okay, you're going to use it to find the angle. So based on this formula, you needed to find the length of the u, length of v, and the inner product. And you try to simplify. But of course, we're not guaranteed under the time pressure, you always do the computation correctly, right? But if you show all the formulas you need and the ideas, then you get the maximum, the maximum partial credit. Okay, so let's find out the length of u. It's -1 square, 3 square, 4 square. So it's going to be square root of 1 plus 9 plus 16, square root 26. Unfortunately, this is not a perfect square. Okay. This is a 5 square, 2 square plus 1 square. So 25 plus 4 plus 1, square of 30. And then dot product. Okay, the dot product will be -1 times 5 plus 3 times 2 and plus 4 times 1. So I'm going to get a -5. I'm going to get a 5. I'm going to get a 4. 6. -5, 6 plus 4. So that's just a 5. So cosine theta is going to be 5 square root 26 square root 30. I think you at least you can simplify a little bit. Square root 10, because square root 26 is 2 times 13, and here's a 2 times 15. So you can take 2 out, right? And then 13 times 15. That's the irrational number. Anyway, so this is a number guarantee it's less than 1. Okay. And so theta, how can I express the theta? Theta is just arc cosine. This is not a good number. You can only estimate the angle. Okay, so that's it. All right. Now, in three-dimensional space, we have another product. I should emphasize that in three-dimensional space, okay, because that doesn't work in the high-dimensional space. Okay, in three-dimensional space, we can define A cross B. Okay, the product of two vector U cross V. That's called the cross product. Okay, of two vectors. Okay, how do you define it? Without using mathematical formula, right? How do I define? We define the following way. So this is vector A, that's a vector B. So use the right hand, you rotate. This is supposed to vector, yeah, come in this direction. Okay, so that is A cross B. So you know the direction of the vector, okay, cross product, but you also should know the length. If this is the angle theta, okay, if this is the angle theta, then I just needed to know how long it is because I already know the direction. Okay, so this vector is perpendicular to A and B. And the orientation is in the direction, use the right hands. Okay, now why I can do that? Because in three-dimensional space, that's only one direction you can choose, which is perpendicular to A and B. Okay, in three-dimensional space. But in high-dimensional, maybe, you cannot, unless you have more vectors. Okay, if you're given two vectors, only in three-dimensional space, you can have a one unique direction line perpendicular to those two vectors. So this vector is on the line perpendicular to A and B. And all I needed to know is the length. So the length is going to be the product of those two and times sine theta. Okay, so that's it. So that is not the very way to express the cross product. The reason is I still want to know the components of this vector, right? I don't get the components of the vector. I only did get the description of this vector. Okay, I know how long it is. If I know the angle, and now given two vectors, I can determine the angle between A and B. I can also find the length of A and the length of B. Okay. But I want to know the components. Here's another way to do. You can call the theorem, depends on which one is definition. Okay, then the other one is called the theorem. If you use the other one as a definition, then this one is called the theorem formula. Okay. All right. So the idea is here's the result. Okay. So if we have an A, I'm going to use A1, A2, A3. B, B1, B2, B3. And the cross product, we can compute it formally using this 3x3 matrices. So A1, A2, A3, B1, B2, B3. Okay. How do they formally? Because IJK are vectors. A1, A2, A3 are numbers. Technically, theoretically cannot put together. Okay. Because in a matrix, all the things should be the numbers. All the elements should be numbers, not the vectors. I just say this can be defined formally. I just say. Yeah. So this is going to be expand like this. A2, A3, B2, B3, I minus A1, A3, B1, B3, J, K, A1, A2, B1, B2, and K. Now this is a vector, right? And each component is 2x2 determined of 2x2 matrix. All right, so that way, we prove that the length is going to be, yeah, it's using mathematics, you can prove that. We can show this is a perpendicular, okay? Indeed, it's perpendicular to A and B first. Second, the length of this vector is going to be the length of A times the length of B times sine theta. Okay, so that's how we find the, yeah. And we can use this cross product to find sine theta. Okay, I'm going to take a look at an example. Okay. So if A is going to be 2, -3, 1, and B is going to be 4, 1, and 3. Okay. We want to find out A cos B. Now, if a theta is an angle between A and B, okay, what is the value? What are the value? Cosine theta and sine theta. Okay. Anyway, so we have to find, in order to find the cosine theta, we have to find the dot product. In order to find sine theta, we have to find the cross product. Right? So first of all, anyway, let's find the length. The length is going to be 2 square plus -3 square plus 1 square. So it's 4 plus 9 plus 1. It's a square 14. And that is 16 plus 9, 25, 26. Okay. It's not a good number. So then A dot B, this is going to be a number. It's 2 times 4 plus -3 times 1 plus 1 times 3. So that's gonna be 8. All right, so I'm gonna get a cosine theta. Cosine theta, according to the formula, I get 8 square root of 14 square root of 26. Okay. I keep this number here. I don't want to simplify it. Because each is an even number, you can take 2 out. So this will be square root of 7, square root of 13. Okay, if you want to simplify it. All right, in order to find sine theta, I can use the formula directly, but I don't know this angle. I think this angle is between 0 and 90 degrees. You can find the sine theta directly using cosine theta, right? Do you agree, right? But you can also use a cross product to verify. Okay. Yeah, let's find the sine theta in a different way. So the cross product, okay, I, J, K, and the first vector is 2, -3, 1, 2, -3, 1. The second vector is going to be 4, 1, 3. So I get -3, 1, 1, 3, I minus 2, 1, 4, 3, J plus 2, -3, 4, 1, K. Okay. So we get -3 minus 1 is -10. And 6 minus 4 is 2. And this will be negative. Okay, 2, oh, that's positive. 2 plus 12, 14. Okay, that's cross product. Okay. So sine theta, remember, sine theta is the length of the cross product divided by this, right? So we can get, okay, it's a -10 square, -2 square plus 14 square. Okay, it does not look like we're going to get an answer here. Square root of 14, square root of 26. All right, I'm going to simplify it. So each of them has a factor of 2. So I can take a 2 out. 5 square plus 1 square plus 7 square. I take a 2 out, right? 2 times 14, 2 times 1. Okay. Yeah, it's an even number, so I can take it out. So it's that's right. So it's here is a square root of 7 square root 13. So I'm going to simplify the top one, 25, 1, 49. Okay. So it's 5 and 75. Right, square root of 75 is 3 times 25. So it's 5 square root of 3. All right. So we get 2 different values. Now, sine theta, cosine theta. So we want to check our formula is correct, we may check whether sine squared theta pi plus cosine squared theta is going to be 1. So let's recall what is the sine. It's a 4, right? So we have cosine, it's a 4 square, right? Yeah, because the numerator is 4. Okay. Plus 5 square, 3 square. Okay. So this will be 16. 75. Right? And here's a 7 times 13. I needed to use my calculator. Okay, I hope I'm right. Okay, 16 plus 75. That's gonna be 91. Oh no, it's not. 7 times 13. 91. Okay, that's correct. Okay, sorry. So that means the formulas we're using above, we did not verify, right? You know, cross, yeah, that should be okay. All right, that's good example. Yeah, so now we so now let's focus on lines and planes. All right, lines and planes in the space. So technically you can, given 2 points in the space, I can uniquely determine line, but 2 points do not uniquely determine plane. The 2 points uniquely determine line. So the point A, point B, there's only one line going through there, right? Now, how can I describe it in the space? Yeah. How can I describe it? I can, what I'm going to do is here. Here's the origin, right? That's origin. Okay. So I can describe an arbitrary point using the following method. I can take an up, not necessarily point A here. I just use a, yeah, I can use A, right? Then I add, that's a B, right? That's 2 points here, right? A and the B. So I want to add this part. This part is actually is going to be this is from here to here. This is vector is from A to B, right? Okay. So you want to make it longer, short. It's the same direction. This is supposed to be TAB, T times AB. If yeah, T is some number. So this point P, okay, OP can be described by OA plus T times, I think, AB. Yeah, AB is a vector in the space, but More precisely, this should be the equivalent representation of the vector from A to B. So, so this vector, okay, if this is the vector, is a representation, that vector. So I'm going to call it V, yeah, equivalent representation of AB. Okay, so then I'm going to I'm going to change that. I'm also going to change this. Okay. This one I'm going to call it A. Okay, O from OA. Okay, A is just OA, no problem. V is equivalent representation of vector from A to B, right? Then this should be A plus T times V. Okay, so this expression describes all the points on the line. Okay, it describes all the points on the line. Okay, because V is yeah. So V is V is this vector. I'm sorry for this is this vector. T times V is, yeah, let me draw the, yeah, this is a T times V. This is a V. Okay. So this is how do we this expression describe all the vectors landing on the line. Okay, starting from the origin. Okay, so this is called the vector equation for the line. It is called, yeah, it's called the vector equation of the line. There are many versions. That's why we don't call it the vector equation, just a vector equation. A vector equation. Okay. It's called the vector equation for the line. Okay, so how do we find it? I think you just needed to find a vector representing a point on the line, which is A, and then also called another vector is called the direction of the line. Okay, V is the direction of the line. Okay, V is the direction of the line. And right, how do we find the equivalent representation for the vector from A to B? You just take the difference of the corresponding components, right? Coordinates. So let's take a look at some examples here. Okay. So here's the example. So we have point A, 6, -5, 2. And another point B, 1, 4, 3. Okay. Find an vector equation for the line passing through these 2 points. Right? You don't need to withdraw. You don't need to, yeah, draw the line. Okay, it's not necessary. Right. So first of all, you need to find the right. You need this. Oh, you need to find the vector. One vector representing a point. Okay. Then you also needed to find the vector equivalent representation of the direction of the line, right? So then you can describe an arbitrary point on the line. So if this is the point AB, then V is equivalent to the vector AB, right? V is the equivalent representation of the vector from A to B. Okay, or just find this too. So you draw the picture, then you know what they're going to do. So A is going to be OA, which is just 6, -5, and the 2. Okay? Very clear. Then the vector AB, okay, the vector equivalent to vector AB. V equivalent to the vector AB is just a difference of the components. 1 minus 6, 4 minus -5, 3 minus 2. Okay, which is going to be -5 and the 9 and the 1. Okay, that's a vector V starting from the origin and ending at this point with coordinates -5, 9, 1. All right, so a vector equation, we're trying to describe an arbitrary vector here. Now that vector sometimes we denote by R, okay? So R is going to be A plus TV. Right, so that is going to be 6, -5, 2 plus T, -5, 9, and the 1. Right, that's the equation. Now you can also express it in the following 6 minus 5T, -5 plus 9T, and 2 plus T. That's fine. So that's called the vector value function. All right. If we write or we put R in the form X, Y, Z, okay, then we get 3 equations. The X coordinate is determined by 6 minus 5T. The Y coordinate will be -5 plus 9T. So Z coordinate will be 2 plus T. So if you don't want to mention the vectors, you have to describe the components of the point on the line using those 3 equations. Okay, those called parametric equations for the line. So parametric equation essentially just a vector equation. Vector equation put all together using notation of the vectors, use the notion of the vectors to describe. Okay, but if you want to describe each component of the point on the line, you get 3 equations. Those are 3 equations called parametric equations. So there are many versions to describe. Okay. Now let's go to the equation again. So this is A plus TV, right? Okay. So I'm going to, yeah. So this is here's X, Y, Z, and here's this point X naught, Y naught, Z naught, and plus yeah. So this is a component, this is a component, then plus T. Okay, I can use the same notation ABC. Okay, so here's what I'm going to do. I'm going to let X, Y, Z and A, X naught, Y naught, Z naught, V, A, B, C. That's okay. Then you have this identity, right? So more general, you get X equals TA, Y equals TB, Z equals TC. So this is a parametric equation in general form. Now, I can also solve for T from each equation. So T can be expressed as X minus A naught divided by A. T can also express as, right, each of them. Right? If we solve for T, you can get T into this equation. So in other words, we have this identity. Right? So this is the equation for the points on the line, right? If this is a point, and here is arbitrary point X, Y, Z, then that's the vector V, right? Kind of, right? So X, Y, Z must satisfy this equation. And this is called the symmetric equation. Okay, this equation is called symmetric equation. They're called equations of the line. Okay, when you ask to find the symmetric equation of the line, that must be in this form. Okay, so we go back to the above problems. So where it is. Yeah, so we have this, right? 6 minus 5t. Okay, so x is 6 minus 5t. Y is going to be, I forgot, negative 5 plus 9t. Z is going to be 2 plus t. Okay, so there's a parametric equation for the line, but they can also describe it in the same in the symmetric equations. As the symmetric equations will be x minus 6 divided by negative 5, you solve for t, and y plus 5 divided by 9 z minus 2 divided by 1. So this called symmetric equations. So for a line, you have three ways to describe. Another way to describe is okay, so three different ways to describe. Okay, vector equations, symmetric equations, parametric equations. Yeah, three different type of equations to describe. Yeah, three ways to describe a line. Okay. So next, how to describe a plane in the space. Okay, how to describe plane in this place. So in the three-dimensional space, right, have a coordinate system here. And I have a plane, right? So now you're going to describe it. So this is a plane. I needed to talk about, right? I have to find a way to describe the points on the plane, right? Some kind of relationship among those. That cannot be arbitrary, right? X, Y, Z cannot be arbitrary. That related. How find this equation, right? This is like a research subject. Right? If you never learned this, right, you have to figure it out by yourself. That's how we make the science, right, or mathematics progress, right? Okay, so we have to constantly try to solve some problems. And in general, okay, if we after you complete the training in the PhD program, you're more ready to do some kind of research in any place. Okay, when you do when you work in for a company, right? You cannot always do the things you're asked to do. Sometimes you have to be creative and discover something new, right? So you can. So like this problem, okay? So now you look through all the books, you learn, and that's it, right? So you have to find a way to describe it. And it's a plane in three-dimensional space. So to describe it, you have to fix another point. Right? So the plane passing through that point. Right? Now, this is origin, right? So this is a vector R. I'm going to use a vector to describe it. And this is a R naught, okay? We have to introduce a notion of a normal vector. A normal vector is a vector perpendicular to the plane. Okay. So let n dot be a normal vector. Okay. That means the vector perpendicular to the plane. Okay. Next is how to find it, right? So suppose you have this normal vector. Then you get, so then R minus R naught. Okay. If R represents a point in the plane, then the difference will be the vector lying in the plane. So that should be perpendicular. So that should be equal to 0. Okay. So this is a way to describe the plane. Okay. And if we want to use the coordinates, right? So if R is x, y, z, right? And R naught is going to be x naught, y naught, z naught. And the normal vector is used A and B and C. Then the difference of those two vectors will be, right? It'll be x minus x naught, y minus y naught, z minus z naught, the dot product, A, B, C. Okay, right? So that is going to be just A times this, B times this, and C times this. Okay, this is supposed to be what? 0. So we get the equation for the plane. So this is the equation in 3 variables, A, x, y, z. It's a linear equation. So we have a name for that. Okay, we have named that. This is still called the vector equation. Okay, and we have named that's called the scalar equation. Okay, of the plane. Okay. Now, after you simplify, sometimes you modify, like you get AX plus BY plus CZ, and you move everything to the right-hand side, right? You can say, if you don't want to move everything to the right-hand side, you get AX0, X naught, BY naught, CZ naught. This can be simplified by the D, denoted by B, right? So the equation you will get X plus BY plus CZ plus D equal to 0. All right. So there are many different forms. This is a general form. And sometimes you're given equation in this form, you can get a normal vector, right? The components, the coefficients A, B, are X, Y, Z that give you the components of the normal vector. All right. So here's a good problem. Let's try to figure it out. So we have a plane. The plane passes through 3 points. A, 1, 3, 2, B, 3, -1, and 6, and C, 5, 2, 0. Okay, find an equation. Now, equation in any form. I have two different forms, right? Find the equation for the plane. So 2 points uniquely determine line in the space. 3 points uniquely determine a plane. Right? The image, right? So you should be able to find equation for the plane because the plane is uniquely determined. Okay, how can I do that, right? So this is a plane, and you have A, B, C, 3 points here. Okay, I needed to find equation for the plane. I need a 1 point in the plane. I need a normal vector for the plane, basically, right? If I know the vector, normal vector, then I'm fine. How can I get a normal vector? Question. How to find a normal vector? Yeah, cross product. So this is a coordinate system here, right? So so you find the vector, let's try. I'm going to use whatever the notation, because this is I'm going to call the U. U is a equivalent a representation of A and C from A to C, okay? And another vector, V, it's equivalent to from A to B, okay? A to B is from here, right? Then the cross product, right? So the normal vector is a normal vector, okay? Right, so let's find out. So I'm going to get U. U is a equivalent representation of the vector from A to C. And so you just take the difference of the component A and the C. So it's a 5 minus 1, 2 minus 3, 0 minus 2. Okay. So that is going to be 4, -1, -2. All right, so that will be 3, -1, 6, 5, 2, 0, 1, 3, 2. Okay. And then V is going to be 1 minus 3, 3 minus -1, 2 minus 6. I think it's 2 minus 6, 1 minus -1, 1 minus 3. Okay. So I get -2, I get a 4, I get a -4. All right. Okay, so let's finish this quick. So U cross V, it's I, J, K. All right, 4, -1, -2, -2, 4, -4. All right, so I'm going to get the first one. All right, so that is going to be 4 plus 8 is 12. -16 minus 4, so -20, so plus 20. and 16 minus 4 and minus 2, it's 14K. So anyway, so this is a vector perpendicular to the plane. So you don't need to normalize it. So this is going to be 12i plus 20j plus 14k. You can divide by 2 if you want. Okay, and I think you can use one of the vectors to choose one vector, right? So R naught, you can use any of them, right? So I'm going to use the point A, 1, 2, 3, right? 1, 2, 3. So that's OA. 1, 2, 3. 1, 3, 2. Sorry, 1, 3, 2. Yeah, 1, 3, 2. Yeah. So you have this. Then the vector equation will be R minus. That's it. So that's called the vector equation. Okay. If we want to put more details there, then that will be x minus 1, y minus 3, z minus 2 dot 12, 20, 14, 0. Okay, that's called the vector equation. If you multiply this out, you can change it to 6, 10, 7, a smaller number. Doesn't matter. So you will get 6, x minus 1, and 10, y minus 3, 7, z minus 2, 0. Okay, that's called the scalar equation. Okay, you can also get minus 6, minus 30, minus 14, right? And then so here's a minus 50, 0. So that's another equation. Okay. So there are several ways to describe there's several ways to describe this plane.